Hello guys, so this is the second part of the review for test 3, and here I'll talk about chapter 10. We talked about 3 types of testing: goodness of fit, independence test, and test for homogeneity. But I'm only going to ask you to know independence test because it's actually done pretty much the same way. So goodness of fit is the first concept that I want to review. Okay. What is the main object? What is the main goal of a problem that deals with goodness of fit? Well, you will usually be given a set of data. So this data right here, I just made it up. But let's say that's what we have. And you're going to call this observed data. We want to know if this data fits relatively well with the expected distribution. Okay? And more often than not, the expected values you need to compute. And that's where most of the mistakes actually happen. So let's say this is my data. I need to find these expected values. How would I do it? Let's say it says that all of these proportions for each of the categories should be the same. The first thing that you need to do is find the total. Okay? So in this case, the total will be 100. Okay? So that's 100 observations. And then let's say the problem says all of these proportions are the same. Then what is your expected number that's going to go in each of these cells? Well, it will be 100 over 6, right? Because we have 1, 2, 3, 4, 5, 6 categories. Okay? 100 over 6, and let's see, how much is that? So 100 over 6 is 16.6 repeating. So I would just keep it like that in your calculator. If you go to your, let's say, edit, and if you go to your L2, I would just do 100 over 6 for all of these entries. Okay? So once you have that done, you need to figure it out if your observed data fits relatively well with the expected distribution. Now, before we do this, technically we need to check that all of these entries are greater than or equal to 5. Okay? If they are, then we can conduct the goodness of fit test. All right? Now, what is your null hypothesis always going to say? The null hypothesis will always say that the data fits our expected distribution. Okay? So data fits the expected distribution. Okay, and then alternative will say, well, one or more of these proportions are different, or in other words, it doesn't fit. It's not consistent. Oh, so data is not consistent. That's one way to say it. Okay, with the expected distribution. Now, the most common mistake that I see happening with expected values. So let's say you computed your 100 over 6, which we said it was 16.6 repeating. A lot of times I see students putting into these cells 0.667 as the proportion. You can't do that. No. The numbers that you need to put in the expected values should be relatively close to the ones that you have with observed. Okay, so that's not what's going to go in your expected values. So once you have that done, put observed values in L1, expected in L2. Okay, now for those of you that use TI-84 calculator, you have a command on your calculator that will be goodness of fit, and I believe it's chi-square, something like that. And then you can run your command, you can run your test just using that command. Okay? Now, if you don't have it, then we need to find chi-square of the data. Okay? Chi-square of the data is found by summing observed minus expected squared divided by expected. Or, on your calculator, you would have to do this one right here. You would have to sum up L1 minus L2 squared divided by L2. Okay? That will produce chi-square of the data. That's what we call it. And we need to compare that to the chi-square from the table. and I will provide that table value on the test. Okay, so what do we do once we have these values, these two? Once you have your values computed, if the chi-square of the data is less than chi-square of the table, okay, so it sits somewhere over here. So here's the picture that goes with the chi-square distribution, right? Your chi-square of the table value sits right here. And we always have a right tail test. So this area right here represents the unexpected, the unusual events, right? So if your chi-square of the data is less than chi-square of the table, it sits somewhere here in the not so unusual region, then what does it mean? We fail to reject. Fail to reject H0. Basically saying, yeah, the data is pretty consistent with our expected distribution. In other words, think about it this way. If this is your chi-square of the data, then this piece right here represents the area under the curve to the right of chi-square. Well, that's pretty large. So that is your p-value way bigger than alpha level. So we'll fail to reject. Okay. Now, what if we have chi-square of the data sits right here? If it's greater than chi-square of the table, then we reject the null. Reject the null. Okay? If it's sitting right here, that means the area to the right under the curve is smaller than alpha level, right? So that's equivalent to saying that p-value is small. We reject the H0. That means the observed values don't exactly follow the expected distribution. Okay, so this is your test for goodness of fit. How well does the observed data fit our expected distribution? And again, if you need to use your TI-83 calculator, you might want to rewatch this one video that I made for this chapter, okay, that talks about the calculator commands over here. But if you have TI-84, then you have a little bit of an easier time computing these values, and you can just use p-value. Okay, so what about test for independence? In test for independence, we're always interested in two variables, and your null hypothesis will always say that they are independent. Okay, one of the most common mistakes that I see happening is that students just mix them up and say that the two things are not independent for null, and for the alternative they'll say that they are dependent, but that's not how it goes. Okay, for null hypothesis, always say they are independent. Alternative will say they are not independent. Okay, then you will be given a table of values. These are your observed values. Again, I just made them up here. So how do you do this? I would go to my calculator and put it into a matrix. Oh, I'm gonna turn it on. Oh, come on. Okay, so you go second matrix, and let's add it matrix A, and the size is 2 rows by 4 columns. Okay, so what are my numbers? 20, 30, 15, 25, 10, 21, 18, and 24. Okay? Alright, and then you can compute the values, the observed value, the expected values by hand, but you actually don't need to. If you go to your test, and it's all the way on the bottom, chi-square test, that's included in both TI-83 and 84 calculators. And you run the test. So observed values go in A, expected in B. You do not need to plug anything in there. The calculator will compute these values for you. So let's just go ahead and calculate it. Okay, and if you go back to your matrix and bring it out, you'll see that the computed values are already there for you. Now, technically, we should check that these expected values are all greater than or equal to 5, and they are, so we're good to go. Okay, so let me just run this test again. So let's say I'm dealing with these numbers. I say that 2 variables are independent, and the alternative is they're not independent. I'm going to run this test, Okay. Let's see. Here I get chi-square and I also get p-value, right? Now, the chi-square of the table, I'm going to give it to you. But the conclusion here is exactly the same as before, for goodness of fit. If chi-square of the data is less than chi-square of the table, then we fail to reject. Okay? Do not reject H naught. Okay? If chi-square of the data is greater than chi-square of the table, then we reject H naught. Okay? What does it mean in the context of the problem? That means the two variables are independent. This means not independent. There's some sort of relationship between the two. Okay, so I think this test is actually a little bit easier than goodness of fit, because all you have to do is plug in the values in your matrix, then in the right side, right, row by column, then run the test, retrieve your chi-square of the data, or look at the p-value. You can also do that. Let's take a look at it. So p-value here is pretty large, 0.323, right? So no matter which alpha level I'm giving you, one of the usual ones, this is pretty large. So looks like here we will not be rejecting the null hypothesis, right? So it looks like the two variables are independent in this case. Okay, all right. So this is the end of the second part for review for test 3, and the last one about correlation and linear regression is coming up in a minute.